Good morning, everyone. So today we are supposed to revise the topic of isothermal and adiabatic process. Okay, and if we have to limit ourselves only to isothermal and adiabatic process, I think most of the questions, if we only are only two processes, are simple application of formula, which is not so complicated. But I thought before we go into isothermal adiabatic process, which itself is not too many things, let's understand something which goes into understanding the process. So I think, see, when we talk about uh, thermodynamics, I think one way kinetic theory of gases forms the important basis of thermodynamics. So you recall something about what is kinetic theory of gases. You recall something we did in case of kinetic theory of gases. What is the key part of kinetic theory of gases?
And there's motion and all that.
So kinetic theory of gases, basically what I say, okay, if a gas is contained in anywhere, if the gas is at some container, if a gas is available. See, kinetic theory of gases works on principle we assume that all gas molecules are tiny little like elastic balls. Okay, and those tiny elastic balls are there at wide separation, and when they move inside a container, they undergo elastic collisions with the wall of container. And if we apply same Newton's law of motion principle, when they undergo collision with the walls of the container, they'll exert pressure. Okay, so treating just like using Newton's law of motion, which we apply to one object, we apply to all gas molecules. And if we calculate pressure, okay, and how this pressure gets related. So it is calculation of pressure, assuming gas to be tiny little elastic particles, and they are widely separated. So they have, so basically when they move around, they are not affected by presence of other molecules. There's no force of attraction repulsion between the particles. So interatomic or intermolecular forces we neglect because they're widely apart. So if those forces are not there, only forces acting is due to collision. So in between the collision, no other force acts, they keep moving in the straight direction. So what is the important outcome of kinetic theory of gases? So kinetic theory of gases, it relates pressure and volume to what? It relates pressure and volume to kinetic energy. So kinetic energy, if we find pressure and volume product, come as a square of the velocity of RMS velocity of the particle. So PV, but ideal gas PV is also related to temperature. So what we infer from kinetic theory of gases, temperature is nothing but a measure of kinetic energy of all gas particles. That's the important part of understanding of kinetic theory of gases. It relates temperature to kinetic energy of all molecules put together. And that we define. So what is kinetic energy? So suppose that's a relationship. So temperature, important part, temperature is a measure of kinetic energy of all molecules put together. Second thing, when we talk about internal energy, another term we come across, internal energy. Understanding of internal energy also important before we proceed to all processes. What is internal energy? See, we talk about in first year, most cases when we talk about mechanical energy. What does mechanical energy mean? Mechanical energy is equal to kinetic energy plus potential energy due to conservative forces. And these conservative forces come because of force of attraction repulsion between two particles. Okay, and we understand it is the force of potential energy depends on how far apart they are. So in case of gas also, can we extend the same principle? Yes, here also when we calculate internal energy, it is based on the similar principle, but only in case of gas, the difference is we assume the potential energy to be zero. Because in gas, we assume in case of, unlike liquid and solid, what is the key difference in gas? Unlike liquid and solid, the distance between interatomic distance or intermolecular distances are much smaller. Hence, potential energy becomes very significant. In case of gas, why it is a gas? Because a small mass occupies large volume, and interatomic distances are large. If interatomic distances are large, I can ignore kinetic energy, potential energy. So internal energy is nothing but kinetic energy. And we just talked about kinetic energy is something proportional to VRMS square. If we take in aggregate, what is VRMS? I think just quick recap of VRMS. All particles might be moving at an instance with different velocity. What is VRMS? If all of them move with the same speed, what is the speed all particles should be moving so that their kinetic energy is same as kinetic energy of sum of kinetic energy of all particles. Okay, so VRMS is that's the indication. So it gives an idea. So rather than looking at multiple magnitudes of velocity for each particle, will have a different one. Actually, no two atoms or molecules will have exactly the same speed or magnitude of velocity. So that's VRMS. VRMS is a measure of kinetic energy. So when we talk about internal energy is kinetic energy. So kinetic energy can be expressed in terms of VRMS. But we also said VRMS is related to temperature. So it relates internal energy to temperature. That's the outcome of kinetic theory of gases. So what is temperature? Temperature is an indication of internal energy. Internal energy is sum of potential energy plus kinetic energy. Potential energy taken to be negligible. So what we understand from internal energy is kinetic energy. But kinetic energy we can measure in terms of temperature. So temperature is a direct indicator of kinetic energy of all gas molecules put together. And how do we relate the kinetic energy? Now, next we come to, unlike, in case of first year also, in case of motion of particle, we studied first translation motion and then we also studied rotational motion. And in case of rotational motion, in case of translation, any object, if it is extended object also, all particles undergo same displacement and same velocity. And we have kinetic energy, something like this. But in case of object, which is extended object, it can also rotate. So it can also have rotational kinetic energy. So similar thing applies in case of molecule also. If it is monatomic, it can only have translation kinetic energy. If it is diatomic polyatomic, it can also have rotational kinetic energy. And since both energies involved, internal energy in case of monatomic gas will have only translation. In case of diatomic polyatomic, it will also have rotational energy. And that we get captured in form of internal energy. So what is internal energy of the gas? All of you should recall internal energy gas. Before we discuss internal energy of gas, let's get a mental picture of what happens in case of monatomic, diatomic, and polyatomic. So suppose we have 3 containers, or maybe 3-4 containers are there. So let's look at what are the 3 containers. All 3-4 containers contain different gas. Let me take 4 containers. And let's try and understand what are the 4 containers contain and what is the mental picture of what happens inside the container. This is one third container, this is another 4th container. So let's say in one container, all containers are maintained at the same temperature. We find all are the same temperature. So one of the container contains, say, helium gas, other contains neon gas, third contains hydrogen gas, and fourth gas some methane or something. So what will happen, see, if you get a mental picture, what will happen in case of helium and neon? Helium and neon are monatomic. So if we have to look at mental picture, it's like a dot. Helium and neon will be like a dot. And because of temperature, they are free to move. Which direction they can move in all 3 directions. And they enjoy their freedom. So they have the freedom to move in all 3 directions. Particle will move in all 3 directions. And that's why called degree of freedom. It has freedom to have move all directions. They move in all 3 directions. So they'll have energy in all 3 directions. Okay. So this particle, it can have kinetic energy in this direction, translation kinetic energy, translation kinetic energy. But since it's like a particle, its moment of inertia is negligible, it will have no kinetic energy. But when I compare helium and neon, if the temperature is same, on an average, kinetic energy of this atom and this atom will be equal. But does it mean they'll move at the same speed? VRMS will not be same. At a given temperature, both will have same translation kinetic energy. In fact, if we compare the translation kinetic energy, all 4 of them, this monatomic, again monatomic but heavier molecule, and this is diatomic and polyatomic, all of them will have same translation kinetic energy. That's the equipartition of energy indicate. But even at the same kinetic energy, what does it imply? The one which is heavier mass will move slower. So compared to helium atom, this is moving faster. And this also, this will move. Since mass is more, it will move slower. But kinetic energy will be same. But what will happen in case of hydrogen atom? If I have to get a mental picture of hydrogen atom is something like this. Two molecules kept connected together. So they will have translation, but in addition to translation, there are three different axes. It will have rotation also. It cannot rotate here. There's no rotation energy, but it will keep, as it moving, it will keep rotating also. Really enjoying their freedom. They're all not only, but this is something, all directions, that they'll rotate like this, it'll rotate like this. And that's called degree of freedom. In this case, it can rotate. This is something like this. I can visualize as four different molecules, something like this. So in this case, what will happen? It will rotate in all three directions. So that's what we call. So what is internal energy? So internal energy, I'll write in two forms. Internal energy only due to translation. Only due to translation, if we have translation, so all three will have same. Only due to translation, the internal energy is 3/2 nRT. What do we understand from here? If we have any gas, it doesn't matter whether it's monatomic, diatomic, or whatever gas it is, if we know the number of moles it has, and if we know the temperature, it only depends on the temperature. Okay, whichever way, the pressure may be different, volume may be different. This will be the kinetic energy due to translation. But what is the total energy, which also includes rotation? Total energy of n moles of gas at temperature T is equal to F/2 nRT. So this is the, I think, background what we have coming from kinetic theory of gases, understanding of internal energy, and to some extent, yes, Vignesh.
Sir, it's 3/2 NRT for all because despite being monatomic or diatomic, they can all undergo translation in three directions, right?
Yes. The degree of freedom as far as translation goes, so it'll have same. Okay.
Okay.
Okay. But total energy, in addition to this, they will also have something like this. This is trying to get a picture of this. In addition, they will have rotation. So if just assume, if I have a monatomic molecule or monatomic atom, this monatomic atom, this has mass m, and there is a triatomic molecule. Okay, triatomic molecule. This also has mass of the molecule is m. Both of them will have same VRMS if the temperatures are same, monatomic as well as polyatomic. But what will happen in this particular case was the same. It will have additional energy on account of rotation as well. So if you recall, in case of rolling, when object rolls down, we calculate now there's a translation kinetic energy and rotational kinetic energy. So why they do have additional energy? Because they have additional degree of freedom, and which they use that degree of freedom, and that's what. So I think, I hope this part is clear. So first part of understanding is understanding of internal energy, and why internal energy comes in form of a temperature. Is it kinetic energy? Yes, it is kinetic energy. Does temperature indicate kinetic energy? Yes, temperature indicates kinetic energy. How do we get that relationship? We get the relationship of kinetic theory of gases, which relates product of power pressure. We express pressure in terms of VRMS. And since these are two P and V is in terms of RMS, since this is proportional to T, the T also is proportional to the square of VRMS. That's the relationship. Hence, we end up getting internal energy, which is sum of kinetic energy of all atoms or molecules in form of temperature. It's a state function. It doesn't matter how did we reach that state. So that is important part to understand. Now we come to thermodynamics. What is thermodynamics? Heat flow. So heat flow, so even before go into equation, let's understand, suppose, how do we visualize thermodynamics? We can visualize thermodynamics. There's some gas which is enclosed. We can always take a piston view. The gas is contained in a cylinder, which has a piston kind of thing, and the piston is free to move. It has no friction at all and is airtight. Okay, just imagine, so this is in a steady state. What will happen if I give heat energy? Heat is a form of energy. So when I give heat energy, I think logically you can think, I have given the heat energy. Where does this heat go? Because all energy cannot be created or destroyed. Where does energy go? So then we start thinking, and that's a understanding of thermodynamics. And if you think, where would this heat go? Either this energy will be absorbed by the atoms or molecules of the gas. If they absorb this energy, what will happen to them? Their internal energy will increase. Or this energy may get transferred to the surrounding through the motion of the piston. So what happens if the piston gets displaced from here to here? What has happened? This gas, the piston moves, who's moving the piston here? The gas pressure is moving the piston. Gas molecules are doing it. So energy which is given in form of heat, logically it makes sense either this energy is retained by the molecules or atoms of the gas, or this energy is get converted into work done. So that's the equation. Heat in is equal to work done by the gas, or heat absorbed by the gas in form of internal energy. And that's a major part of the chapter, is good understanding of this part. If we understand these three terms involved here and their relationships, how each are calculated, we'll get a good understanding of thermodynamics. This internal energy, I think this is something we have come from the previous slide. What we understand this internal energy? For a gas, this internal energy is F by 2 nRT. And we have understood what this internal energy implies and why it is in form of temperature, and it's a state function. Case Henry state temperature term, so it just depends on the temperature. How the temperature has been reached is not important. So I hope you understand what is state function. It doesn't depend on the path kind of thing. What is work done by the gas? Work done by gas calculation is simple. So basically, work done, we know force into displacement. Who is doing work? Gas is something. So gas is exerting pressure, and pressure is gets converted in form of a force acting on the surface of the piston. So what is the force acting? Pressure into area. So pressure is P, force into pressure into area. If the expansion takes place, work done is positive. So when is Q positive? Let's get the mental picture. What is the Q positive? This is positive. Heat is flowing into gas. So we write this, what heat given to gas is positive. And what is work done positive? When gas does work. How do we visualize positive work done? When the piston gas expands and piston moves like this. This is the positive work done. The work done by gas is taken positive when it is positive, when gas expands. Okay, so this into dx. That's the work done. Okay, the pressure force into displacement. But what we understand, what is A into dx? A into dx is nothing but change in volume. That's why P dV is nothing but work done. So we understand what is work done. P dV is work done. This is change in internal energy, and this is heat supplied. And we have done in case of, there's another chapter, heat transfer and all. Heat transfer, we typically what we understand, heat transfer, we have done something in case of solid. What we write? We write delta Q it can have three effects. Heat has three effects. What are three effects it has? It can change temperature, it can change state, or it can change the dimensions. So if it changes state, it changes temperature. What is this equal to? We write something like this, MC delta T. What is C here? C is specific heat capacity. That's what we use in case of solid. So we try to relate how heat and temperature are related, and heat and temperature are related through heat capacity. But when we talk about gas, how is heat related to change in temperature? Here, heat related to temperature, this is not a constant relationship. Here, there's no work done. But in case of work is also being done. So what will happen? This relationship between these two will also depend on what is the work being done. And that's where we say depends on, as the temperature changes, during this process of change in temperature, how much is work being done? If there's a lot of work is being done, what will happen? Then more heat is required. If no work is done, then less heat is required to change your temperature. So when we talk about, there's two changes here. First of all, it is dependent on how, along with change in temperature, what else is happening in terms of work. So it depends on that part. And when we write NC delta T, there we deal with mass, here we deal with number of moles. So this changes in N, and this we call as molar heat capacity. Since it is number of moles, this has to be per mole. Then we multiply by mole into delta T. And this value, this term depends on the process. So we can write for different process, we'll have different value. So two specific process, now we come to process part. Okay, so this is part we understood. What exactly we mean by process? Let's try and understand processes. Process mean there are typically we deal with the three parameters P, V, and T, and sometimes we can write density also inverse of volume and all. So for a given amount of moles, and is fixed for most processes. So when we have this thing, when the process, these parameters change. The process is, when we vary the parameter, what is the relationship addition? What is the way we are changing the parameter? Are we following a particular way in changing the parameter? And which particular, so how the parameters are varied in relation to each other, that defines the process. Let's try and understand the process. See, suppose this pressure is here. See, suppose this piston is massless. If piston is massless, outside pressure is atmospheric. Inside the gas pressure also will be atmospheric. I hope that part is very clear. So if piston has no weight placed on it, if outside it is whole thing kept in the atmosphere, pressure inside is atmospheric. How do I increase the pressure? If I put some weight here, if I gradually increase the pressure, if I dump some sand here, if I keep adding sand here, what will happen? Slowly keep adding sand mass, granule by granule, pressure inside will keep increasing. What is the pressure inside? Pressure inside will be equal to Q naught plus whatever weight we have placed on the piston divided by area. So how do I vary the piston? How do I vary the pressure? By adding or releasing weight on the piston, I can change the pressure. So that's how we can change the pressure. Okay. So suppose I have kept some sand here. I'm not changing any amount of sand. I start supplying heat here. So when heat is supplied, some change will happen. But if the weight on the piston is not changed, what will happen? Volume will change, but pressure will not change. Volume will change and temperature will change as you supply heat. So how do I follow a constant pressure process? If I do not change the weight I have placed on the piston during the change of other parameter, it becomes a constant pressure process. So, I'm getting some sense of what is constant pressure process. Second thing, what I can do, if the piston is here, I fix the position of piston and then I supply the heat. When I fix the position of piston, it means piston cannot move. It means the volume cannot move. So when first case pressure is same, so let's try and understand what will happen if the pressure is kept constant. So if I have PV diagram, so PV diagram. So what I'm saying now, if in this case, I started with there was some initial pressure and there was some volume. So what will happen when I start supplying heat from here? When I supply heat from here, I find the piston has moved up. When the piston has moved, volume has increased. Volume has increased, but pressure has not changed. How would the process look like? The process will look like this. So you understand, you should be able to visualize when we say constant pressure process, we should have clear understanding what does constant pressure mean. Similar way, can you tell me how would you carry out constant volume process? By keeping the position of piston fixed. How would I carry out constant temperature process, isothermal process? Can you think of if I have to actually carry out in form of an experiment, isothermal process? How would I carry out isothermal process? What I need to do to carry out isothermal process? Can someone think of how do I carry out isothermal process? What does isothermal process mean? I am varying these parameters, but I am keeping T fixed. What is constant pressure process? I am varying this parameter such a way that this P is not changed. That becomes constant pressure process. If I don't change V, it becomes constant volume process. We understood how we do it. So similar way, how do we carry out isothermal process? Can anyone think of what is the way? I have defined how to carry out constant pressure process. I have defined how to carry out constant volume process. Can we define how to carry out constant isothermal process?
P into V should be constant.
Pardon me? No, that's it. See, you're telling mathematical relationship. I'm giving physical significance. So suppose I have piston here, gas here. I want to carry out an isothermal process. It means something has to change here. How would I carry out the process?
Should be the surrounding where temperature is constant.
So basically what has to happen, one way of carrying out constant temperature isothermal process, if it is kept in air, if the vessel is made of a conductor, if it is a good conductor, if suppose it is thin, what is this piston here? This is made of thin copper. If it is thin copper and I carry out process slowly. So what will happen? Suppose even if I'm supplying heat from here, I put a burner here, but whole thing is exposed to air. Will that temperature, and I supply the heat very slowly and allow, since if it is a conducting material, will the temperature of gas inside the container will rise? Even if I'm supplying heat. If it is kept in a what you call a container which is a good conductor of heat, outside temperature and inside temperature will always remain same. So when I keep in a good conductor, it becomes an isothermal process. How do I carry out adiabatic process? If I convert whole thing in insulating material, if I surround the whole container by insulating material, the heat cannot go, heat cannot go out, heat cannot come in. So suppose I insulate everything and add some more weight here. Will the parameters change? I have insulated all sides of the wall. I have added some more weight here. I have dumped some more sand here. What will happen? The pressure will change, volume will change, but what will happen? That would be an adiabatic change. But if I add sand here and I keep this no insulating material and it is exposed to air, if I add sand here, that will also lead to compression. But in that case, pressure will increase, but that compression will be isothermal compression. Are you following the difference between the two? Gayatri, have you whatever mentioned, is it most of it is making some sense or not?
Yes, sir.
Huh? So I'm trying to make you understand not only the relationship, what you see in terms of mathematical relationship, try to relate what would it imply, what would it look like. Pranav? Pranav Soma?
Yes, sir. Yes, sir.
Are you following this?
Yes, sir.
This equation, does it make logical sense? Are you able to relate? Is it just a formula? You understood what sense it makes?
I've actually understood quite some of it.
Quite somewhere?
Yes.
Good. So there's something, so we relate also, what does it happen? See, it makes logical sense. When we give heat, where would this energy go? So that's energy balance is a conservation of energy. We have to understand this term. I hope you understand this term. We need to understand this term. This term also is nothing but work done. We have defined what is work done is PdV. So this is something we have to a total work done. We integrate, we get work done. And what is dq? I give a relationship. dq is something. See, purpose we write dq. It will lead to change in temperature. Here there's no change in phase. We don't deal with change in phase. In case of solid, heat can also lead to change in phase. So either of the two. Here it is something like this. And we have. I hope you have understood why C can be different. And if we think of it, does it make sense that C value? There are two different processes. One is a constant volume process, V constant process. In case of V constant process, what is work done? No change in volume. Work done is zero. In that case, whatever heat I'm supplying, everything going into change in internal energy. Okay, so it will lead. But second thing, if I have constant pressure process, if pressure is constant, I'm heating it from here. What is happening? The piston also moves. Work also gets done. So what will happen for same change in temperature? I need to supply more heat. And that's why we find Cp has to be greater than the common sense. It makes Cp has to be greater than Cp. Do we see a logical reason why Cp has to be greater than Cp? There's a logical explanation. So we understand this equation, we understand this term, and I hope we have some understanding of what does process mean. Okay, and processes, but how we vary these parameters, and those change in parameters we can express in terms of mathematical relationship. So easy to define: constant pressure process, constant volume process, constant temperature process, constant dq is equal to 0, adiabatic process, and other processes. Okay, now come to isothermal process. Okay. Isothermal process, as the name suggests, we keep the temperature to be constant. It means the gas is always in thermal equilibrium with the surroundings. So it is kept in a container which allows free flow of heat, and typically isothermal processes are carried out slowly. Why it need to be carried out slowly? So that there's adequate time for heat transfer to take place. So isothermal processes are typically slow process, and it is in case of thermal equilibrium, typically in thermal equilibrium with the surrounding. Thermal equilibrium means it keeps changing, it keeps exchanging heat with the surrounding, so that its temperature is same as the surrounding temperature. And definitely it need to involve a container which is a good conductor of heat. So as the process becomes simple. So what is thermal process? T is equal to constant. When T is equal to constant, it's very simple. PV becomes constant. So when we draw PV curve, it becomes a rectangular hyperbola. Okay, so we understand this part. Second part, we need to understand if for same number of gas. So for same number of gas, basically N is same. For same gas, I can draw three different isotherms are drawn. If you have to figure out between the three of them, which one is higher temperature? T1 is higher, T2 is higher, or T3? How do we figure it out? We understand T, N being constant. If N is same, T is proportional to product of P and V. So here we find if we draw a vertical line, all three V are same. The one with the higher pressure will have higher temperature. So what we infer from here, okay. Second thing, sorry, but we'll come to that part also later. What we infer from here is the isotherm. Any point, if I have this isotherm here, any point on this curve, the temperature is same, T1. But any point above isotherm, temperature is greater than T1. Any point below isotherm, temperature is less than T1. So if we move above isotherm, temperature rises. If we below isotherm, temperature falls. If we change the process in such a way that PV remains always in the same isotherm, temperature will remain constant. Okay. So that is something we can easily infer. Now coming to this part here. In terms of the basic energy equation, in this case, delta U will be 0. The temperature is not changing. So whatever heat we supply to the gas in case of isothermal process, entire thing gets converted into work done by the gas. You supply heat, gas will do work. If you draw away heat, gas will contract, work will be done on the gas. It will do negative work. Okay, and what will the work done? Suppose we have from here, if I move from point A to B. So what is the process if I move from A to B? Is it expansion or contraction? In this case, volume is increasing. It's a case of expansion. So this is isothermal expansion. And what will be the work done here? Work done will be the PdV. So PdV is a summation of all these narrow stripes. What is summation of all these narrow stripes? Area under PV curve and V axis. So what is work done? Work done is area under PV curve and which axis? V axis. That's the work done from A to B. Okay, so work done is PdV. And if you have to calculate work done, we have PdV, P and P can be substituted what? P is equal to nRT by V. So I integrate this term, I get the work done. And that's very simple formula, and we can visualize also. It is integration of V, and work done is equal to nRT log of V2 by V. And that's equal to heat supplied also. So this are, I think, what are the few points we need to, isothermal is a very simple thing. Delta U is equal to 0, T is equal to 0, it means delta U is 0. This implies heat given is equal to work done. Work done is equal to PdV, and we substitute P in terms of V, which is nRT by V. We integrate this, we get the work done, nRT log to the base E, V2 by V1. That's the work done. Area under the curve, we understood anything above the curve is temperature rises, anything below temperature falls. So this is a point we need to know in case of, okay, so what is slope of PV curve? So when you look at this, what you're finding here, slope everywhere is negative. And as we move from here, the slope is steep and this is flat. Everywhere negative, but this part is steeper. And as we move here, it has become slope has become less. So I hope all of you are clear of the term steep and flat. So if you are walking here, you will find it easy to walk. If you are walking here, you'll find it difficult. So it's steep and flat. So how do you find slope of PV curve? We find the slope using from this equation. PV is equal to constant. So that can be written as PdV, if we take its derivative form, is equal to V, dP is equal to constant. And slope is anything with slope is dy by dx. But here on y-axis is P, x-axis is V. So slope, which is typically equal to dy by dx, slope in this case will be equal to dP by dV. What is dP by dV equal to? From here we simplify, it gets equal to minus P dot. That's the slope. Negative term of the wherever any isotherm cannot have positive slope, it will have any negative slope. So what we find here, as we move from here, what is happening as we move from here to here, P has decreased. As the pressure is decreasing, the slope magnitude is decreasing. That's why its slope becomes flatter and flatter. The slope of the PV curve is equal to minus P. Above isotherm, temperature rises and falls. Okay. What is adiabatic process? Adiabatic process also nothing much, pretty simple. Adiabatic process, delta Q is equal to 0. If we use that equation delta Q, it means work done becomes to change in internal energy. Temperature is changing. What is change in internal energy? Change in internal energy can be written as NCV delta T. Value of CV is equal to, we should remember, the value of CV is equal to F by 2R. It comes directly from DU. DU is equal to F by 2 nRT is equal to NCV delta T. Okay. So CV is equal to, this is work done. And I'm not going to derivation. How does pressure and those things vary? Okay. This is the expression. PV raised to power gamma is equal to constant, and gamma is called adiabatic constant, which is equal to Cp by Cv. And you should know for monatomic, diatomic, suppose we write this table, all of you should be able to do it very easily. I think suppose we have to write for mono, dia, and polyatomic. What is the degree of freedom? Degree of freedom is 3. This is 5, and this is 6. What will value of Cv? Cv is equal to F by 2 R. So this will be 3 by 2 R. This will be
5 by 2 R, 6
Yeah,
3
so
R.
6 by 2, 3 R. And then what is Cp equal to? Cp is equal to Cv plus R. So add one more here. This becomes 5 by 2 R.
5 by 2,
So 7
7
by
by
2
2,
R and 4.
5 R.
And gamma value is the ratio of the two, which is equal to 5 by 3, 7 by 5, and 4 by 3. What you're noticing here, the gamma is decreasing. Which value has the highest gamma? Monatomic has highest gamma, which is roughly 1.67, and this is 1.4, and this is 1.33. So gamma is decreasing. Now coming to, so this is something, this is pretty simple. In case somebody forgot, I think we'll have quick recap. And now we come to this equation. Adiabatic process, this is a term. I hope other things you have followed. Now let's look at okay. This NCV delta T, PV per gamma is equal to constant. Can you find the slope in this case again? Slope I can write in two different ways. One is PV raised to gamma is equal to constant. So whenever we have this kind of, for small changes, we can also write like this. For small changes, dP by V, what is the coefficient power of the term? Plus gamma dV by V is equal to 0. This is something I think we use for small changes. So even for errors approximation, we use the same. And this comes from differentiation only. So again, slope is what? What is the slope here? Slope is again dP by dV. And in this case, what we find the slope is equal to minus gamma times P by V. So slope is multiplied by gamma. Since gamma is greater than 1, slope is steeper than isothermal gamma. So okay, let's say adiabatic expansion. That's what will happen in case of adiabatic. Let's try and understand what is the significance of this term. So this is the point from here. Expansion will go like this. So one, if we have an adiabatic expansion, at this point itself, this is P and V. At this particular point, if I draw a tangent, the tangent will have a slope equal to minus P by V. But if what I have written, this is isothermal expansion. And when we have adiabatic expansion, since if I draw a tangent at the initial point, this will have steeper. So beginning itself, it will have steeper slope. And this every point is go like this. So what will happen whenever we have from the same point, if we have isothermal process and have adiabatic process. Since we are starting from the same point, P and V are same, but still there's a difference in slope because of the gamma term, which is a steeper slope. Adiabatic curve will have steeper slope. Isothermal will have lesser slope. Adiabatic will have steeper slope. So again, let's have, so in this case, this is V1 and this is V2. So once we have, okay, let me just erase this off and then come to that point again. So this one is isothermal expansion and this one is adiabatic expansion. I hope all are clear expansion. Both cases starting from the same point, final volumes are same, but final pressure and temperature will not be same. It's easy to infer which case the pressure, this final pressure is isothermal will have higher pressure or adiabatic will have higher pressure. Clearly we see when we have same final volume, isothermal process final pressure is greater than final pressure of adiabatic process. And since final pressure is greater, temperature also is greater. So what will happen in case of adiabatic expansion? Here, if we started with T0, this will end up with the same temperature T0. But this has same volume but lower pressure, has lower temperature also. This will have a temperature which is lower than T0. So what we can infer from here, when we have adiabatic expansion, temperature falls. Temperature will fall. Other way we could understand why temperature is falling. As we move from here, we have moved below the isothermal curve. As we move below the isothermal curve, temperature will fall. So adiabatic expansion, temperature falls. What will happen in case of adiabatic compression? From same point, once we have adiabatic compression, other we have isothermal compression. So can we draw those curves also? So here, this is again similar way. Let's try and understand what will happen in case of. So this is a point, a starting point, and it had certain value of initial pressure and volume. Okay, this is V1 and this is P1. I have drawn, is easy to draw. Suppose I compress it to half the volume. So what happened for initial volume? I compressed it to half the volume. So this V2 is half the 2. So this is half the 2. If volume becomes half, it's easy to understand what will happen. Pressure will become double. So what will be shape of isothermal curve? Isothermal curve may go like this. This is isothermal compression. This is isothermal. How would be adiabatic compression? Can we starting from the same point? Can we draw the shape of adiabatic compression now? Compression means it will get compressed, and which volume? Same V2. What will the shape? All of you can think and draw in your mind. What will the shape of adiabatic compression? Adiabatic compression, will it be this like this or like this? Adiabatic compression we have done already. So this is the slope it has. Adiabatic will have always the greater slope. So if you're walking like this, adiabatic slope, magnitude slope will be greater. Hence, adiabatic curve will be something like this. It will be about this. So with this will be adiabatic compression. So when it reaches the same volume, the pressure in adiabatic pressure will be much higher than whatever pressure we would have obtained in case of isothermal process. This will be steeper. And what will happen to temperature when we have adiabatic compression? The temperature rises. And this is how, in a way, in your refrigerator. Your refrigerator, you notice, you go behind the refrigerator, you will find it is really very hot. Why does it get heated up behind the refrigerator?
Because it's taking the heat from the stuff inside, air inside.
No, so reason the temperature rises, yes, the gas comes to compressor, and compressor suddenly compresses the gas. It has a compression. So gas comes at a low temperature. What happens when you suddenly compress it? It will undergo adiabatic compression. Any sudden process, adiabatic. When it gets compressed, what will happen is temperature rises. And if you leave that gas in the surrounding, if you just suppose you have some gas here, just think of what is happening here. Suppose I have some gas here. This gas is at what temperature? This gas is at temperature of 5 degrees centigrade. Okay. And what is the outside temperature? Outside temperature is 30 degrees centigrade. What will happen is suddenly compress this gas. Sudden compression is always adiabatic. Why is sudden compression always adiabatic? Can someone think of reason why sudden compression is adiabatic? So what happened? We have compressed, this piston has moved from here to here. So we have compressed the gas. Why sudden compression is adiabatic? Sudden means there is no time for heat transfer to take place. So suddenly from here we have compressed it like this, and then we leave it here. The piston will leave it here. When we suddenly compress it, what will happen? Will the temperature remain as 5 degrees centigrade? The temperature may rise substantially, and the compression is so severe, it may rise to something like maybe say 50 degrees centigrade. Suppose because the compression temperature has risen to 50 degrees centigrade, and then we leave it here. What will happen after this? This is 50 degrees centigrade, this is 30 degrees centigrade, and the container is a conductor. What will happen after this? It will start radiating heat. Immediately start radiating heat, and if surrounding, you feed that the temperature in the surrounding air rises, it gets such a, and as the heat radiated, if it allow it to remain for some time, finally temperature will drop to 30. So suppose I compress it like this and leave it here for some time. What will happen? Finally, volume remaining same. Volume will not change now because I have fixed the place of the container. It will come back to the same point. It will come back to the same temperature. That's what will happen here. I hope this point is understood. Khyati, are you following this? Khyati? Grishma?
Sir?
Yes, are you following? Is anything going into your head?
Yes, sir.
So you can, if you want to make sure that it's going into your head, you should have some check to make sure it has gone into your head. How can you check? One way of checking is take your head weight before the class and check your weight of the head after the class. And if you find the weight has increased, you can assume yes, something has gone into the head. Anyway, so I hope we have understood, and this is what happens. So isothermal process, I think these are key points we need to understand. more in terms of not only in terms of formula. I hope all of you have some sense of what is happening. In case of additive expansion, temperature falls. I hope all of you understand this curve will be steeper. It will end up with the pressure much higher. It will end up at higher temperature also. In case of adiabatic compressor, temperature rises. That's what happens. That's how the fridge works. There's a compressor which compresses suddenly to much smaller volume. The temperature shoots up and temperature becomes, initial temperature was lower than surrounding temperature. Final temperature becomes higher than surrounding temperature, immediately start radiating heat and temperature start falling. That's why the heat transfer from inside the fridge takes place to the surrounding air outside the fridge. Okay. That's a compression curve. Okay. Now let's look at some numericals. I think once we understand numericals should be much easier to solve. So all of you read the question and see that how do we go about solving this question. So we identify what kind of process. It is isothermal process. So what is work done in isothermal process? Isothermal process, here now P dV, we substitute P value and we find work done is equal to nRT log of V2 by V1. So what is N here? N is equal to 1, R is 8.3 and T is 273 and log of V2 is 11.2 and this divided by 22.4. And we can inverse it, so it becomes minus 8.3 into 273 into log to the base E2. Log to the E base 2 is roughly 0.7 and we can find. This is a pretty easy one. So let's look at what is bulk modulus of ideal gas at pressure, isothermal bulk modulus. Do you recall what is bulk modulus is equal to?
Delta P by minus delta V by V.
Delta V by V. You know, either put is delta V by V. So if I have to find bulk modulus for isothermal process, I'll use this process. PV is equal to constant. And since I need dP and dV term, I will differentiate this. It becomes VdP plus TdV is equal to 0. So what is, from this equation, what is dP is equal to? dP is equal to minus PdV by V. I substitute this value here, I find bulk modulus nothing but pressure. And same thing if I do in case of adiabatic process, it becomes PV was again is equal to constant. In that case, we can write as dP by P plus gamma dV by V is equal to 0. And what we find the bulk modulus in this case is gamma. You can easily do that. Okay, this is also application of the formula of adiabatic. Suddenly, what does suddenly mean? Whenever you come across a sudden word, it is adiabatic. Why sudden implies adiabatic? Sudden means there's no time for heat transfer to take place. Or during this time the process has taken place, time is so short that amount of heat transfer is negligible. Okay, initial pressure of the gas will be. So this is simply P1 V1 is equal to gamma is equal to P2 V2 raised to power gamma. So this question you can very easily solve. Gamma value is given. These are simple questions. That's the saying. I think substitution and solving numericals in adiabatic process and isothermal process should be pretty simple. It should be pretty cakewalk. So what is the answer? All of you can get an answer. What is the answer you get here? All of you?
Get 32 times.
Hmm?
32 times.
So P1 V is to power 5 by 3 is equal to P2 and 1/8 of the initial volume V by 8. So pretty simple. P2 is equal to 8 raised to power 5 by 3 into P1, which is nothing but 32 P1. So they are pretty simple questions, simple substitution. Something similar also, this also very same. Same thing written in different form. In place of pressure and density, density is given. What is density? Density is inverse of the volume. When I write in terms of volume, I write P is equal to gamma is equal to constant. If I have to write density term, density is nothing but proportional to 1 by volume. I can write P by D raised to gamma is equal to constant. So this one will be P by D raised to power gamma is equal to P dash by D dash raised to power gamma. So pretty simple, but they are pretty, this is most of the question are fairly straightforward. try to find temperature. So PV gamma, if you remember, PV gamma is equal to constant. That's enough for all cases. Since it is relationship per constant kind of thing, I can always substitute P is equal to some constant into V raised to power T. P is equal to K times T by V. So it is equal to T into V raised to power gamma minus 1 is equal to constant. So see that all of you can easily get your answer. So T1, V1, gamma minus 1. So gamma minus 1 is equal to 2 by 3.
2 by
Is equal to T2, V2 raised to power 2 by 3. So typically you find all terms are, they have perfect cube root. So it becomes easy. So they're easy to solve. I think they're pretty easily can get answer. Okay, let's answer this question little quantitative. Two identical samples are allowed to expand isothermally and adiabatically. Which case work done will be more or less? Can we compare the relative value of work done in adiabatic and isothermal expansion? So if not, we can draw a figure, PV diagram. Can we draw a PV diagram in this particular case? Expansion. So let's draw a PV diagram here. Is expansion. So this from the initial point, this was the initial point. Expansion means volume will increase. So but we have seen already, if volume becomes double, pressure will drop to half. So that would be roughly the shape of isothermal curve. If this is the shape of isothermal curve, what will be the shape of adiabatic curve?
It will be steeper, so more area
Yeah,
is there.
so once you draw the shape, it becomes easy. The shape will be like this. This is isothermal and this is adiabatic. Okay, now we are talking about two identical samples are allowed to expand thermally. What they have not mentioned, it is implied to the same final volume. When work done more, work done is area under the curve. Which curve has more area? In area under PV curve and the V axis. Naturally, we see here in case of isothermal, area is more. Work done in isothermal process is more than adiabatic process. More in isothermal process. So unless we understand, realize this one, we not with the formula, we have the graph very easily can inform. Next one. So try and visualize what the shape of PV diagram would look like in this particular case, what would happen. And indirectly I've done this question earlier, some 10 minutes back. See that we can apply the same thing here and solve. Cylinder is suddenly compressed. This is the initial point. So suddenly compressed means what? What does suddenly imply here?
Adiabatic.
Adiabatic. Okay. So suppose from this point, if I draw an isothermal curve, if this was my isothermal curve is easy for me to draw. Because if I take the volume to become half, pressure has to become double. So this is my isothermal curve. Adiabatic curve will be much steeper. So what will the shape of adiabatic curve? Let me draw the adiabatic curve also. So adiabatic compression will be something like this. It will go something like this. So this is how the compression has taken place, adiabatic compression. Now question is, and then maintained at the same position. What does the meaning of same position mean? And what does the meaning of maintained mean? Same position means if
It will radiate,
Volume
right,
is
sir?
constant.
volume does not change, this volume will remain same. So this volume does not change the process, and maintain means it is allowed, what is implied here, it is kept in the same surrounding. If it is kept in the same surrounding, if the temperature was T naught here, this has become T naught plus, it has increased. So what will happen, it will follow, and it will finally, if it exchanges heat with the surrounding, its temperature will come back to the same T naught. Following which process? It will follow a constant volume process because its position is maintained. So what will happen? So from here, when during the process, during the time the position is maintained, it will come like this. This is what will happen during the time it is maintained slowly. So what is happening during this process? What is happening to temperature? So what is happening to pressure here? What happened to pressure during this time? Pressure will drop and temperature also will drop. With passage of time, this implies from here to this point, A to B implies what is happening during passage of time. So passage of time, basically it exchanges heat, basically, or transfers heat to the surrounding until it reaches to the same temperature. Till which temperature? Say air temperature, till it reaches surrounding temperature. So this also I hope is easy to understand. All of you can easily follow. So pressure will, so you can see from here as to be, pressure will fall. So if you have to visualize something, I was telling earlier, compression. So there's a compressor, you compress it suddenly, then leave the piston there. What will happen if you leave the piston there? Inside the pressure, inside the piston, the pressure will slowly drop. Pressure will decrease, but will it come back to the same initial pressure? No, it still will be higher than initial pressure. It will twice the initial pressure if the volume is compressed to half the volume. But it will drop, and temperature also will drop. We are moving below the isothermal curve. Whenever we move particularly downwards, temperature will fall, particularly for temperature will rise. How do we calculate work done in adiabatic process? How do we calculate work done in adiabatic process? There's no need to calculate work done. In case of adiabatic process, work done is equal to minus delta U. The calculation of change in internal energy most of the time is much simpler. So in this case also, rather than calculating work done, I will calculate change in internal energy, which is equal to minus F by 2 NR T2 minus T1. That's what it is. So whenever we talk about work done in case of adiabatic process, work done is equal to, since delta Q is equal to 0, work done is equal to minus delta U minus change in internal energy. Here the temperature is rising, internal energy is increasing, hence work done will be negative. That's why it is compressed. Compressed means always expansion, work done is positive, compression, work done is negative. Very easy to solve. And it is diatomic gas, hence value of F is known. And value is given, gamma is given. Actually, both the things are not necessary. One of the things were enough. Both are given. Okay, so I think that's what it covers most part of isothermal and adiabatic process. So I'll stop here. Some of those who have doubts, you can ask, and we will continue. If you have some more doubts, we'll continue in the evening session. So evening session both for this as well as any doubt related to previous topic. Okay. I hope you got your mind.